Okay, now let's come to the definition of strains, and in this course we will be dealing with infinitesimal strain theory. That is, we will not be dealing with large deformation, large displacement of the bodies in this course. According to the infinitesimal strain theory, displacement of the material particles are assumed to be so small that the geometry and the constitutive properties, both of them, of the material at each point in the space are assumed to be unchanged. Accordingly, infinitesimal strain theory assumes that the displacement of the bodies are very, very small. That is, the body has moved to a new position, and that change or that displacement is very, very small from its previous configuration. Secondly, the deformation or the displacement gradients are very small. So the body has moved very little from its previous position, as well as the deformation or the strains are very small in the bodies. In this particular slide, the term deformation and strain admit the same meaning. Now let's define strains. Consider an elementary cube ABCD, and let's say due to the action of forces, point A has moved to a new location by displace such that its horizontal displacement is u and its vertical displacement is v. Point B has been displaced by magnitude delta ub and in the horizontal direction, and in the vertical direction by magnitude delta vb. Point C has been displaced by in the horizontal direction equals to delta uc, and in the vertical direction delta vc. And let's say the sides of this cube is delta x, delta y, and delta z in the z direction. In the limiting case that delta x and delta y tends to 0, strain in the x direction are defined as the change in the length of the segment AB divided by the original length of the segment AB. That is, the change in length of the segment AB is delta UB, and the change in the original length of the segment AB is delta X. And in the limit delta X tends to 0, this shrinks down to the differentials, partial U divided by partial X. Similarly, epsilon YY is equals to the change in the segment AC divided by the original length of the segment AC. So epsilon YY comes out to be partial V divided by partial Y. And the shearing strain gamma XY is nothing but equals to the change in Y direction with respect to the segment along the x-axis plus the change in the x direction with respect to the y length. So you will come up with that the shearing strain is equals to change in V with respect to change in x plus change in u with respect to change in y. Note down that gamma xy is the total angular distortion of this element, which is also called as engineering strain. However, for theoretical computation, we use tensorial shearing strain epsilon xy, which is actually the average of the engineering shearing strain. For a three-dimensional body, the strain tensor looks like this, which composed of 9 independent strain components. If there is symmetry of the strain components, like epsilon xy is equals to epsilon yx, similarly epsilon xz is equals to epsilon zx, and epsilon yz is equals to epsilon zy, so then there are 6 independent strain components that fully defines the strain state of a point. So now then we have 6 strain components that fully defines the state of strain of a point. For mathematical computations, instead of using two-dimensional matrices, it is very easy and less time consuming to perform operations on vectors. So we use void notation, in which we represent second order tensors as first order tensors, or in which we represent matrices in terms of vectors. So this matrix of 6 elements, 6 independent elements, can be written down in vector form like this. Looking into the definitions of epsilon xy, xx, epsilon yy, and gamma x, gamma xy, I can also write it down the definitions of strains in the matrix form, something like this, where we have this differential operator matrix as well involved. So I can see here from that epsilon xs is equals to partial u over partial x. Similarly, epsilon yy is equals to partial v over partial y. Epsilon zz is equals to partial w divided by partial z. Similarly, so this is the matrix representation of the strain definition, which can be helpful for calculating strains if we know the displacements in the body, right? Or in indicial notation, I can write it down that each strain component epsilon ij is equals to half of partial ui divided by partial xj plus partial uj divided by partial xi, or half of ui comma j plus uj comma I. Since it's a three-dimensional, if we are talking about three-dimensional body, so I and j both varies from 1 to 2, because there are 3 orthogonal axes involved. So this is the compact form of the strain tensor. Now in mechanics of solid, most of the time we are interested to find out the effect of forces which one part of the body exerts on the other part of the body. And in order to do that, what we do is that we make an imaginary cut in the body, and then we try to find out the forces which are acting on that imaginary cut. For example, if this is a body which is let's say I made an imaginary cut at this particular plane, and I would like to see what are the forces which are acting on this what are the forces of this body R1 which are acting on R2, and what are the forces which are from the R2 are acting on R1. So let's say the resultant of forces on this particular plane on a differential element delta A is delta F. Then in the limit that this differential area tends to 0, we'll get a stress vector, or we also call it traction vector. So traction vector is a kind of a stress vector acting on a particular plane. And we can imagine that if we change the plane, so the magnitude and direction of this resultant force acting on this plane will also change, right? So for example, if I make a cut over here at some inclination, so the magnitude and direction of this resultant force will also change. So it means that the distraction vector depends upon the normal to the cutting plane as well. So let's try to find out what is the relationship between the traction and the normal plane. For this, let's consider a tetrahedron A, B, C, P. Let's say the face A, P, and B is subjected to the stresses sigma xx, sigma zx, sigma yx. Similarly, the other two faces are also subjected to some stresses in three-dimensional frame. The resultant of these stresses components on a face A, B, C is balanced, is equal. The resultant is equals to traction T, whose components in the x, y, and z direction are Tx, Ty, and Tz. And let n be the normal to this area A, B, and C. Orientation of plane ABC can be defined in terms of normal, and this normal can again be defined in terms of the Cartesian coordinate system. So nx, ny, and nz are the x, y, and z components of the normal vector. Let's first of all define or find out the values of the areas A, P, B, C, P, B, and A, P, C. So I can readily see that let's call this area APB to be delta x, because the normal of this area is pointing in the x direction. And we can also see that delta x is nothing but the projection of the area ABC on the x face. So I can also write it down in mathematical form that it is the projection of the area ABC on the x plane, or the on a plane whose normal is along the nx direction. Similarly, delta y is the y projection of the area ABC, and delta z is the z projection of the area ABC. Then apply the equilibrium condition. Let's say apply the equilibrium of the forces in the x direction. So we have that the force sigma xx multiplied by its corresponding delta x area. Similarly, force delta sigma xy multiplied by its corresponding area, and the force sigma xz multiplied by the corresponding area must be balanced by the traction force Tx, which is acting over this delta BC area. So this is what is written over here, the equilibrium condition. I can cancel out delta ABC from this equation, and I'll get this final form of the equation. Similarly, I can apply the equilibrium in the y direction, and I can also apply the equilibrium of forces in the z direction. So now I will have three different equations, and I can also write it down in matrix form as well. I can see here that this is a vector of or the components of the traction vector T. These are the components of the normal vector N, and this is a kind of a second order tensor which relates these two vectors. You remember that we defined second order tensors which operates on two vectors. Okay? So this second order tensor is relating the normal vector to the traction vector. So this is a relationship between the traction vector and the normal vector, and this second order tensor we usually called as the Cauchy stress tensor. Why it is called as Cauchy stress tensor? Of course, it was formulated by Cauchy, and secondly, it defines the forces in the current configuration with respect to the area defined in the current configuration. And I can simply say that the stress tensor sets actually the relation between the traction vector which acts on a plane and the normal on that plane. Again, for a three-dimensional body, stress tensor is composed of 9 different components, and if there is a symmetry, so we will have 6 independent stress components which fully defines the state of stress at a point. Again, for mathematical simplification and computation, we can arrange this second order tensor or this matrix form into a vector form for ease of calculation using the Voigt notation. This kind of notation or representation where we shrinks down the dimension of a matrix is called as Voigt notation. So now we have the complete definitions of stresses. We know what are stresses, we know what are displacements, and we also know what is the relationship between the strains and the displacements. The next thing we need is the constitutive relation, the relations which describe some relationship between the stresses and the strains. For this particular course, we will use Hooke's law. We will assume a linear relationship between the stresses and the strains, and Hooke's law in 3 dimensions looks like this form, where this is the compliance matrix. Now we have the complete definition of stresses. We know the kinematic relations. We have the constitutive relations. Now we are ready to formulate the equilibrium of the body. For that, let's consider a cube, a differential cube of lengths dx, dy, and dz, which is subjected to stresses, let's say sigma x, sigma yx, sigma zx on the x face, and let's say on the other x phase at a distance dx, the stresses are sigma xx plus some change in the stresses, similarly sigma zx plus some change in that stresses, and similarly sigma yx plus some change in sigma yx. Similarly, we have, let's say, the stresses which are also acting on the y phase and the z phase as well. Let's look into the equilibrium of forces in the x direction. Sum up all the horizontal forces. So the force created by sigma xx and the force created by sigma xx plus sigma xx comma x dx, and multiply it with the corresponding areas. Similarly, we have these are also the these stress components will also create some forces in the x direction, so we have to consider it in equilibrium. Similarly, these stress components will also be considered in the x direction equilibrium. And if I put all the forces into equilibrium, plus the body is also subjected to some body forces, some volume forces. As I've told you earlier, that bodies can be subjected to some body forces which are volumetric forces and some surface forces. So let's say this body also has some weight or some magnetic field or some volumetric force. Let's represent it with B, and let's say the component of that volumetric force in the x direction is Bx, and to get the total force, I have multiplied that force per unit volume with the volume of that cube. So this is the equilibrium of all the forces of that cube in the x direction. Simplifying it, I'm getting this kind of equilibrium equation, which is the equilibrium in the x direction. Similarly, I can also formulate the equilibrium in the y direction and equilibrium in the z direction, and I will get for three-dimensional body 3 equilibrium equations. Or in a more compact form, in the indicial notation, I can write it down as partial sigma ij comma j plus bj is equals to 0. Or in compact notation, I can write it down that dot product of the gradient with the stresses plus b is equals to 0, or dot product of gradient with the stress tensor or with any vector field is usually called as divergence. So I can write it down, divergence of sigma plus b equals to 0. So this is the equilibrium equation of a solid body. Now, many times we can simplify the analysis of our 3D physical problem by treating it satisfactorily by a 2D problem, right? So two-dimensional problem in elasticity are of two different types: plane strain, or they can be plane stress. Plane strain is that state. Plane strain state is that state of strain in which out of plane strain components are assumed to be 0. For example, let's take the case of a retaining wall or a dam. The strains in the z direction are approximately can be assumed to be 0. So we can analyze this retaining wall by simply considering the xy section of this problem. Similarly, for a dam, again the change in the strains in this z direction are very small or negligibly small. So we can analyze this dam with satisfactory results by only considering the cross section of the dam in the xy frame. So correspondingly, the out of plane strain components are 0, or epsilon zz is equal to 0. Similarly, epsilon xz and epsilon yz are also equals to 0. We will have only 3 strain components, which are the strain in plane strain components: epsilon xx, which I can calculate using this equation. Similarly, epsilon yy and gamma xy are present. Equilibrium equations. So of course there is no third equation in the z direction because the strains are 0 in that direction. So I can, and I'm only analyzing a 2D structure in xy frame, so I will have only 2 equilibrium equations. The constitutive relations, I can derive it by simply putting epsilon zz this component and this component equals to 0, and I can develop some constitutive relationship which for the plane strain problem looks like this. So this is the stiffness matrix for the plane strain problem. Stresses in the z direction are equals to this particular equation. Plane stress problem. So plane stress state of a body is that state of stress in which out of plane stresses are assumed to be 0. For example, if you are analyzing very thin plate, or let's look into this particular problem in which we have a thin plate with a hole and is subjected to loads which are uniformly distributed through the thickness. So in this particular case, the stresses in the out of plane direction can be assumed to be 0, and I can simply analyze this 2D structure of this plate without sufficiently compromising on the accuracy of the solution. So the out of plane stresses components are equals to 0. The corresponding in plane strain components can be calculated with these particular definitions, and the corresponding equilibrium equations in the xy frame are these two equilibrium equations. Okay.